So I'll continue with the next line coding scheme, which is alternate mark inversion. This I had sketched and had called this as AMI in short, or this was also called as pseudo-ternary, and in fact we had called this as bipolar. Okay, so there are so many names for this kind of line coding scheme. So we'll take the case of bipolar, return to 0, okay, with 50% duty cycle. There, as I told, it could be both return to 0 or non-return to 0. We'll try to analyze with return to 0 scheme, okay, with 50% duty cycle. So just to look back into what kind of logic that is used in AMI line coding scheme is that bit 1 is represented as alternatively plus A and minus A, okay, for the duration 0 to TB by 2, okay, and 0 for other half. So since it's a return to 0 scheme, it is it takes value only for half of the bit duration, and bit 0 is 0 for the entire duration. Okay, so and hence there are three levels: plus A, minus A, and 0. Both plus A and minus A for bit 1 alternatively, if it depends on the previous level. So if the previous level is plus A, the next bit 1 will get minus A. So that hence this is actually is known as level coding with memory. Okay, so it actually flips between two levels, plus A and minus A, depending on the previous bit value, and hence it will have certain memory as well. So that's something special about this. Okay, so this plus A and minus A, as if I take an example of say 1, 0, and 1, if these are bit durations, if I try to plot this again, this is how it will look like. Okay, just for the sake of clarity, this is 1 for half the duration, and this is 0 for another half. Okay, and for 0 it is entirely 0, and for 1 this is minus A on the other way round. Okay, and so on. So that's how you can say that if this is 2 TB, if this is 3 TB, this has a transition at TB by 2, and this is 0. Okay, that's how it keeps on alternatively marking the amplitudes of bit 1. Okay, so let's try to evaluate its power spectral density using the similar process that we have done for other three-line coding schemes. So here g of t is, as it goes for only half the duration, so it's a rectangular function which goes for only half the duration, so it is t over tb by 2, which we have written already as its Fourier pair, as this is tb over 2 sinc of pi of tb over 2. Okay, and to calculate this g of f is known, and we know that power spectral density is square of g of f, so magnitude of g of f the whole square. That will be substituting once we find out the autocorrelation function. So autocorrelation function r of k, again it takes for several cases. Say for k is equal to 0, this is interesting to calculate this part, that we know it's distribution between it's equiprobable combination, so there could be only two combinations that are possible. So one is, as 1 1, and another could be simply 0 0. So if these two are the probable cases, as for half, since 1 1 combination can be either plus a and plus a, another 1 1 combination can be minus a and minus a. So again in turn there will be again these will be distributed equally. I mean the probability of occurrence of all these two combinations again is equiprobable. So again I should split it into another half, which is a into a plus half minus a into minus a. Okay, plus this half. Okay, 0 into 0, as we know we don't send any symbol for 0 and 0, and this is simplifies this gets simplified as simply a square by 2. Okay, a square by 2 plus a square by 2 is a square, and over 2 is on the outside. Okay, so this is for k is equal to 0. We'll try to calculate what will happen for k is equal to 1. Okay, we had never done this, we had only taken k is equal to 0 and k not equal to 0 as the only two cases. But for k is equal to 1, what do you mean by k is equal to 1? You just shift the bit period by 1. So for k is equal to 0 there is no shift. Okay, it's the same signal that we are trying to find out the autocorrelation function. But for k is equal to 1, we just try shifting for 1 bit duration and then find by taking the autocorrelation function. So what would you get? Okay, so this is has to be dealt in little detail. So as we know that R of k is product of all the combinations of an and n plus k into probability of each of these combinations. Say the combinations now will take 4 different values, where an k is 1 now, so I can say this as an and an plus 1, and I'll try to tabulate all these values and then try to feed into the summation. Okay, so for combination of an and an plus 1 could be, there could be 4 combinations, as we know that it could be 0 0, okay, and it could be 1 0, it could be 0 1, and it could be 1 1. Okay, so for 0 and 0, I mean the probability for all these combinations is equiprobable again. So I can say the probability of occurrence of each of these is 1 over 4, since there are only 4 combinations that are possible. For first combination, obviously the product of an and n plus 1 is 0. Okay, and for the next combination, as I know an is 1, and this 1 can be represented again as plus a and minus a for the half duration of time. Okay, and hence there could be another two sub configurations for this representation of bit 1. So I can say that this gets splitted into 2 ways. Okay, this gets split into 2 ways. One, each of these combination has half, then this one combination is half, half of this is 1 over 8. So the combination of these sub configurations will be 1 over 8 of this. So one combination is plus a into 0, another combination is minus a into 0, because another bit is 0 here. So both of the product will result in 0. Just for the sake of understanding, I am trying to take all the combinations that are possible. So similarly for this as well, so this takes two sub combinations. One is 0 into minus a, or 0 into a. For both of these products you will have 0 as a product. But for the last configuration, it's both 1 and 1, and hence the combination could be plus a into minus a minus a into plus a. Note here that, carefully note that both cannot be simultaneously plus a and plus a, or minus a and minus a, because we have shifted just for one bit of duration. So in one bit of duration, obviously if there are successive bits of ones, we will be alternatively shifting between their amplitudes plus a and minus a, and hence we cannot expect for last combination the other two combinations which are which would be a possibility as minus a and plus a and plus a will not happen for k is equal to 1. Okay, so for this case you will have the product as a square, as I told. So all these probabilities are 1 over 8. So as I told, all these probabilities are 1 over 8, half of 1 by 4. This is also 1 by 8, and the resultant of this both products is minus a square. Okay, and hence I can come back in calculating this autocorrelation function. So for all combinations it is 0 except for 2. So those two cases are simply a square by 8 minus a square by 8, where minus a square is the product of two random samples. Pi is their probability, which is 1 over 8, and hence this is a square by 4. Okay, I hope that is clear. All right, so this is for k is equal to 1. Let me take a calculation of autocorrelation function for k greater than 1. Okay, obviously for all negative values also, for I can say for mod k greater than 1, or for k, for all k. Okay, okay, fine. It's sufficient for representation of that last combination. So for r of k, we'll have to do a similar process. The only additional thing that will come, as I told, is simultaneous values of plus a and minus a's. Say, just to make things clear, this is an plus k, and probability of that ith combination. Okay, similar process. So for 0 and 0, the probability is 1 over 4, and hence the product is 0 into 0, and the result is 1 over into 1 over 4, which is 0. And for 1 0, which are taken as next combination, 1 and 0, the probability is again 1 over 4. This gets splitted as a into 0 or minus a into 0, each with probability 1 over 8. Doesn't matter. Okay, the product is also 0, and for other combination 0 and 1, the main probability is 1 over 4, and it can have sub 2 combinations, 0 and minus a and 0 and plus a, with 1 over 8, 1 over 8 as individual probabilities. The probability is 0, and finally for 1 combination 1 over 4, there could be 4 such combinations which are possible. Okay, now for this case it could be a into a into minus a into a, or minus a into minus a. Okay, each with probability of 1 over 16. Okay, so with that I have got this as a square over 16, this as minus a square over 16. So this is minus a square over 16, and for the last combination it is plus a square over 16. So finally summing of all these values, okay, this will simply result in r of k as 0. So all these last terms will obviously will cancel with each other of plus a square minus a square minus a square and plus a square, and with that I will have autocorrelation function for only two, in fact three values, for k is equal to 0, k is equal to minus 1, and k is equal to plus 1. Either it is a left shift or right shift for one bit, you will get similar uh, values for both of those for values of k. So for k is equal to 1, I can say for magnitude of k is equal to 1. So ultimately you will have only 3 terms. So therefore I can say r of k. Okay, so I can say that for all k less than -1, all will be zeros. Okay, all these values will be zeros. Okay, and for k is equal to 0 or k is equal to, yeah, exactly, k is equal to 0, we have calculated this as a square by 2, and okay, there is one k is equal to -1 as well. I have to include that. Okay, say for k is equal to -1, this is minus a square by 4 plus a square by 2 for k is equal to 0, and again minus a square by 4 for k is equal to 1, and for all other combination again it is 0 only. So for all k greater than 1, only for these 3 values I'd be having a non-zero value of autocorrelation function. Okay, so with that I can write per spectral density, okay, as S of f as magnitude of g of f the whole square over tb. This is for Wiener-Khinchin theorem. I'm just rewriting this from minus infinity to infinity r of k e power jk omega tb. Okay, so that g of f that I have written earlier, which is tb over 2 sinc of pi f tb over 2 magnitude the whole square over tb times, as I told, this summation exists for only 3 values. Say for k is equal to -1, say k for k is equal to -1, it's minus a square by 4, it's minus a square by 4, and this exponential will be minus omega tb plus a square by 2 for k is equal to 0, a square by 2, and for k is equal to 1, this is again minus a square by 4, but k is plus 1, so this is j omega tb. Okay, so simplifying this expression, okay, just simplifying this expression, a square can be pulled out, so this is a square times tb, this is tb by 2 whole square, and I'll pull out a square by 4 outside of this braces, so this will be a square, 1 tb gets cancelled, so this is a square tb over 8, and this is sinc square pi f tb over 2. Okay, so what is left inside the braces is that a square by 4 is taken out. So if a square by 4 is taken out, so this will have, I can say that this can be simply written as, okay, a square by 2 is taken out, I'm sorry, a square by 2 is taken out, so this will be 1, so 1 minus half e power minus j omega tb plus e power j omega tb. Okay, that will be left inside the bracket, and this can be further be simplified as sinc square pi f tb over 2, okay, times 1 minus that we know e power j theta plus e power minus j theta is your 2 cos theta, and hence this 2 and this half gets cancelled with each other. What we left is cos omega tb. Okay, and this using a trigonometric relation of 1 minus cos theta, this can be crisply written as sinc square pi f tb over 2. This is 2 sine square omega tb by 2, so the 2 and 8 this will get cancelled with each other, so this will be 4 So this is sine square omega TB, which can be written as 2f TB, 2 pi f TB, and which can be written as simply by f TB. Okay, this is your final expression of path vector density for AMI scheme. Immediately we can list the advantages. Okay, the advantages, one primary advantage very similar to Manchester line coding is that no DC content, correct, because of the product of sine square term there. Okay, and the second important is there is a timing content. Okay, or you can say that RB, as I had written in the earlier class, it's bandwidth, because this contains major lobe. What I mean by this is this is sinc square function. Okay, so sinc square multiplied by this, if I can say, this is simply sinc square pi f TB over 2. So this will have the content in this will be your 2 over TB. Okay, and hence the timing information will be there at, and I need not do that once I have written this in a plot. The timing content is available at 2 1 over of this, which is 1 over twice of TB. Okay, so these are the two important advantages which is with respect to Manchester line coding. And similarly, for long strings of zeros, if I want to say, if there are long strings of zeros, in case of disadvantages, okay, long strings of zeros with respect to AMI, there will be loss of synchronization, because we send, there is no transition for bit 0 in case of AMI. So we are sending bit 0 as no signal at all. So this the problem of loss of synchronization persists like your polar or unipolar NRZ schemes. Okay, unlike your Manchester scheme, there was a transition for bit 0, but since there is no transition for bit 0, you will have the problem of losing synchronization, and there is no self clocking or self synchronization, unlike your Manchester line coding. Okay, that's one of the major drawbacks. Another major drawback is with respect to two power supplies needed. Okay, exactly like your polar, you need to have a dual power supply as plus A and minus A. Okay, so this is also one of the drawback of AMI coding scheme. So basically, to summarize, I'll just summarize the line coding scheme so far that we have studied in specific to this Manchester and AMI. Okay, uh, to summarize, AMI, okay, and Manchester coding have following important advantages. Okay, both of have common. I've listed them already, but just for the sake of clarity, both of these line coding schemes have no DC at, I mean, no DC content, or I can say no energy at DC. Okay, no power or energy at DC. Okay, this is one of the primary advantage which we are seeking for other schemes. Okay, and at F is equal to 1 over 2 TB. Okay, there is significant energy. Okay, even at 1 over TB, at 1 over 2 TB, which is a half of your the frequency or the bandwidth. If you just check with our Manchester line coding, I'll just go back to that, which I had drawn for that. Even for as you can see here, even at although the bandwidth was contained within 2 over TB, even at half of that, even if a quarter of that, you will have maximum energy content in it. Okay, so with respect to that, I can say that even at even at half of your 1 over TB, there is a significant energy content in it. This is nothing but where 1 over TB is actually your clock frequency. You have a significant energy content at even at the half value of your clock frequency itself. So these are the major two advantages of these two schemes in common. However, the problem or the disadvantages of Manchester and AMI takes two parts, where the bandwidth of Manchester coding, okay, is actually twice that of bandwidth of AMI. This is very obvious. We need not calculate anything. This is obvious because of what? Because of there is doublet of pulse in a single period. Okay, for Manchester line coding schemes, there are two pulses in a single bit period, and hence if there are two pulses in a single bit period, obviously the when you compare with AMI, which takes only one pulse for the entire bit duration, obviously the requirement of bandwidth is double than that of requirement of AMI. So this is one of the drawback of Manchester coding compared with AMI. But the advantage of Manchester coding is that Manchester coding, as I have told earlier, Manchester coding does not cause a long strings of zeros. Okay, so it has got self-clocking in it, and hence it does not cause any long strings of zeros problem. Okay, at the receiver. Okay, but AMI definitely it suffers from that. Okay, but same is not true for AMI. Okay, so these are the important summary of these two famous line coding schemes, where there is a trade-off between synchronization and the bandwidth. Whenever you are in requirement of sending clock along with data, you should seek for Manchester coding and pay the price for bandwidth. And if you are seeking for lesser amount of bandwidth for the transition, you should send the clock separately, and this problem of long strings of zeros may create in such transmission. Okay, so even though the prospector density of AMI has a significant energy at f is equal to 1 over 2 TB, which is half of the clock frequency, remember that the derivation of the prospector density that we had done for both AMI and Manchester, we assumed that there is a uniform discrete prob density function for both of them. We have assumed that bit 0, assumed that, remember this point. Okay, we have assumed that a uniform discrete probability density function, okay, for symbols, in the sense say if there are bit 1 is represented as symbol v naught, sorry, bit 0 is represented as v naught and bit 1 is represented as v1. So there is a uniform distribution between these two symbols, where we say that it's equiprobable. So that means that this is half of v minus v naught plus half of v minus v1, which is represented as, this is 0. If I say this as v1 and if I say this as v0, both of them will have an amplitude of half, which is uniform distribution function. So we have assumed this, remember. But when all zeros are sent, when only long strings of zeros are sent by the user, it is not a random signal, right? So it's a definitely a deterministic stream of long zeros which are sent by the user, and hence probably your AMI will not be is not the popular line coding scheme in such cases. Okay, so therefore AMI, okay, is not popular when the user sends long strings of zeros. Okay, so this is definitely a deterministic process from the user, where he is intentionally sending so much amount of zeros, in the sense your the transitions of your unlocked to digital scheme, which has got long strings of zeros. Okay, in such cases, definitely AMI, although it gives definitely a lesser bandwidth compared to Manchester coding, but it fails in handling such long strings of zeros. So we want to have a line coding scheme which occupies less amount of bandwidth, but also must handle long strings of zeros. So the advantages of each of these schemes are considered to generate a new line coding scheme, which will be the discussion in the next session, which is the last part of this line coding scheme, which is actually which gives away two schemes, which generates or which paves the way for discussion of two schemes. One is for European standard, another used in North American standard. These are popular line coding schemes which are used in practice. Okay, so these European standard schemes are called as high density bipolar N line coding scheme, and these North American standard schemes, which are popularly known as binary N0 sequence or BNZS. And accordingly, if there is a sequence of say a long strings of 3 bits, so it is accordingly called as B3ZS. If there are 6 zeros, accordingly it is called as B6ZS, and so on. And similarly with the European standard. So both the schemes are included in your syllabus or curriculum. We will try to discuss in your next session to conclude about line coding scheme.